Welcome to this lecture on simple ideal vapor power cycle. In this lecture, I will be giving a sample problem in this topic. Consider a steam power plant operating on the simple ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascal. The mass flow rate of steam through the cycle is 35 kilograms per second. Show the cycle on a TS diagram and schematic diagram with respect to the saturation lines and determine the following. First, the pump work both in kilojoules per kilogram and in megawatts, the heat input in the boiler in the same unit, heat output in the condenser, thermal efficiency in percent, turbine work output, net power output of the power plant, heat rate, and the back work ratio. So, the important given in these problems are the statement simple ideal Rankine cycle. Therefore, we can use the formula that we have for the simple ideal Rankine cycle that we have in our class. Also, we are given with the steam condition as it enters the turbine, which is 3 megapascal and 350 degrees Celsius. Also, we are given with the pressure at the condenser or the condensing pressure, which is 75 kilopascal. And finally, we are given with the mass flow rate of the steam through the cycle, which is 35 kilogram per second. Since there's only one loop in the cycle, therefore the mass flow rate through all the components is the same. It is 35 kilogram per second. This is the schematic diagram of this given problem. As you can see, we have the simple ideal Rankine cycle. Which components are shown? We have the condenser, we have the pump, we also have the boiler and the turbine. It says in the problem that the steam enters the turbine at 3 megapascal and 350 degrees Celsius. So in this loop here, we have 4 points, important points. First, we have point 1, we have point 2, point 3, and point 4. Point 3 is where the steam enters the turbine, and it is given in the problem that it has a property of a pressure of 3 megapascal and a temperature of 350 degrees Celsius. Also, we are given that it condensed at the condenser at a pressure of 75 kilopascal. For the condensing pressure, it is the same at the inlet and the outlet of the condenser. Thus, at the inlet of the condenser, which is at point 4, the pressure is 75 kilopascal. The same also at the outlet, which is 75 kilopascal, which is at point 1. So this is the schematic diagram for a simple ideal Rankine cycle. It's composed of the pump, the boiler, the turbine, and the condenser. You can also find here in the schematic diagram the work and the heat interactions. First, we have the heat input in the boiler. So this is represented by the Q in. So this heat input can be from your source of heat, which are the coal, fuel, combustion of the fossil fuel, also from geothermal wells, also from nuclear fuel power plants, and it may also come from solar thermal plants. So that is our Q in. So it's the heat source from which we derive the heat source of this entire power plant. We also have here the heat output or the heat rejection at the condenser. So the purpose of the condenser is to cool the hot steam that is coming from that turbine. So as it cools that steam, it releases large amount of heat, and it is represented by this Q out here. So it could be rejected into the atmosphere in the cooling tower, or it can also be released in the nearby river. Another component here is the turbine, which produces the work turbine output. So you can see here that the arrow is going out because it produces work. So that's why it's work turbine output. It is opposite that of the pump, which requires work from the electricity. So that's why the work here is going inside. So it's work pump in. So the difference between the two work is the work net. We also know from previous discussion that the difference between Q in and Q out is also the work of the cycle, or the net work. So also in this cycle, we can represent this in a TS diagram. So the equivalent TS diagram of this schematic diagram is this one. So this is also the TS diagram for a simple ideal Rankine cycle. So you can see here also the various points that is found in the schematic diagram, like point 1, point 2, point 3, and point 4. At point 1, which is the inlet of the pump, the condition of the working fluid here is a saturated liquid. That is why it is found here in the left side of our saturation lines or saturation curve. So this is point 1, and that is saturated liquid. So if it is saturated, it will touch this red curve here. So when it is in the left side, it's saturated liquid. When it is on the right side, it is a saturated vapor. Then it enters the pump. So the purpose of the pump is to pressurize it. So to increase the pressure. So when it tries to compress the liquid, it will raise its pressure. So that's why we can see here that from a pressure of 75 kilopascal, it will reach another point, which is point 2. At point 2, it will have a pressure of 3 megapascal. So this 3 megapascal here is also the pressure of our of this line here that you can see. So this is a constant pressure line, which is equivalent to 3 megapascal. So when you say constant pressure lines, the pressure along this line here is the same, and that is 3 megapascal. So that is why the pressure at point 2, the pressure at point 3 is the same, and that is 3 megapascal, and that is also the pressure of the boiler. So it is now at point 2. This is now called our boiler feed water. So it will be fed into the boiler. So it will enter the boiler. So this feed water will enter the boiler, and it will, due to this enormous heat here in the boiler, it will cause this feed water to vaporize and form a superheated steam at point 3. Now at point 3, it will have a pressure of 3 megapascal and a temperature of 350 degrees Celsius. So at this point, this is also where it will have its highest temperature at point 3. And then it will enter now the turbine. So you can see here, when it enters the turbine, it will undergo an isentropic process. In the same way, here at process 1 to 2, this is also isentropic process. That's why we have here S1 is equals to S2. It means that the entropy at point 1 is the same as the entropy at point 2. Same also with process 3 to 4. This is an isentropic process. But unlike process 1 to 2, which is compression of the pump, process 3 to 4 is isentropic expansion of the steam in the turbine. So it's expand. So the steam causes the expansion of the turbine. So that is why upon leaving the turbine, it will lower its pressure to the condenser pressure of 75 kilopascal. So basically, that is how the simple ideal Rankine cycle looks like, both in the schematic diagram and in the TS diagram. So again, some important things that you have to remember. Process 1 to 2 are isentropic process. That means entropy are the same. Same also with process 3 and 4. That is isentropic process. Another constant property process here is process 2 to 3, which again is an isobaric process. So the pressure at 2 is equal to the pressure at 3. Same also with process 1, 4 to 1. This is also an isobaric process. Pressure at point 1 is the same as the pressure of point 4. It is also worth mentioning that the area inside this green curve here that you can see, or the area of this cycle, represents the network of this cycle. So if you want to have a greater net power output or net work output, you have also to design the power plant in such a way that the area inside this curve, this green cycle here, is larger. So you can do that by doing some changes in the pressure of the boiler and also the pressure at the condenser. So that is the schematic diagram and the TS diagram. So it's very important for you to know that, because it will help you as we go deeper and deeper into the next topic. So now we are ready to get the enthalpies. So the first step in solving problems in vapor power cycle is to draw first the schematic diagram and the TS diagram, because it will help us in finding the different values of the properties at the different points. So after drawing the schematic and the TS diagram, we are now ready to draw. We are now ready to get the enthalpies, and that is our step 2. So to find the enthalpies at the various points in the cycle using steam table or using software. So at this point, I will illustrate how to use the steam table in finding the enthalpies at the various points in the cycle. So as you can see, we have 4 points in the cycle. We have point 1, 2, 3, and 4. So we will start with state 1, or at point 1. So as I mentioned a while ago, point 1 is a saturated liquid because it is designed that in a Rankine cycle, it will always be saturated liquid at the exit of the condenser. Again, that is an idealization only. So it is not necessarily the actual thing that happens in actual power plant, but it is the idea. So that's why it's saturated liquid at the end exit, at the outlet of the condenser, or that point 1. So since it's a saturated liquid, we can get the enthalpy using our steam table. We can get H1 as equals to the enthalpy of the liquid, or HF, at 75 kilopascal. So it's 75 kilopascal because we know that the pressure at point 1 is 75 kilopascal. So that is why we got H1 using steam table as 384.39 kilojoules per kilogram. We also need to find S1 because it will help us in finding S2 because they will be the same. So S1 can also be computed using the same procedure, that is the entropy of the liquid at 75 kilopascal using steam table, and that is 1.213 kilojoules per kilogram Kelvin. Also, we will get the specific volume at point 1, and that is Vf at 75 kilopascal. And that is equivalent to 0.0010373 meter cube per kilogram. So that's specific volume. So now that we have the property at point 1, we are now ready to get the property at point 2. To get the property at point 2, we should know that this is an isentropic process, meaning the entropy at point 1 is the same as the entropy at point 2. That is why S2 is equals to S1. And since we know S1 already, so S2 is also equals to 1.213 kilojoules per kilogram Kelvin. At this point, we can also get the work pumped in, or the work input in the pump. And we can use our formula, which is equals to the specific volume multiplied by the difference of the pressure of the boiler and the pressure of the condenser, or P2 minus P1. So by substituting the value of the specific volume V1, which we already have in the previous slides, and also we are given with the value of P2, which is 3 megapascal. So we just have to convert it to kilopascal. So that's why we have here 3000 kilopascal minus P1, which is 75 kilopascal. So it's always P2 minus P1 we compute for the work input in the pump. So the work input in the pump is 3.0341 kilojoules per kilogram. So we need to convert it into megawatts. So what we need to do is just to multiply it with the mass flow rate. Again, the mass flow rate is given, and that is 35 kilogram per second. And since there is only one loop here in this cycle, the mass flow rate in all the points will all be the same. That's why we have 35 kilogram per second multiplied by 3.0341, which is the work input in the pump. Therefore, we can get the power input in the pump, and that is 106.2 kilowatt or 0.1062 megawatt. Now that we have the work input in the pump, we can also get the enthalpy too by using another relationship, which is work input in the pump is equals to H2 minus H1. By substituting the value that we already have, which is the work input in the pump and also the value of H1, we can rearrange this equation to get the value of H2. Therefore, H2 is just equals to 3.0341 plus 384.39, or that is 387.4241 kilojoules per kilogram. So in that way, we're able to get the value also of enthalpy at point 2. So now that we have the enthalpy at point 1 and also the enthalpy at point 2, we can now proceed with the state 3. As state 3, it is given in the problem that it is superheated vapor, which has a property of 3 megapascal and 350 degrees Celsius. We can use now the vapor table in the steam table. So by going to the superheated vapor table in the steam table, we can get H3 as the enthalpy at 3 megapascal and 350 degrees Celsius. And that is 3115.3 kilojoules per kilogram. The same way, we can also get the value of enthalpy by going to the superheated vapor table in the steam table. So we will have S3, or the enthalpy at point 3, as 6.7428 kilojoules per kilogram Kelvin. Now we will proceed with state 4. State 4 is in a saturated mixture region because it is somewhere between the saturation curve or saturation line. So if it is here in between, it is considered a saturated mixture or a mixture or a two-phase substance. At point 4, if we are going to look at our uh, the diagram, we can find that we only have one property that is known, and that is the pressure. So we need another property, and by analyzing it, we know that process 3 to 4 is isentropic process. So entropy at point 3 is the same as the entropy at point 4. So we will use that in finding the value at point 4. But before that, we need to get the value of H4 by using the relationship that if it is a mixture, we can use this relationship. H4 is equals to the enthalpy of the liquid at point 4 plus the quality of that liquid represented by this X4 multiplied by the latent heat of vaporization at 4 or HFG4, or simply the difference between HG and HF in the steam table. We need to solve for X4 for us to get the value of H4. But before we can solve that, this is where we will use the value of the entropy. By using the same relationship, but now in terms of entropy, we have S4 is equals to SF4 plus X4 multiplied by SFG4. We know that S4 is equals to S3, and we already have S3, and that is 6.7428. Also, we can get the value of SF4 is as equals to the entropy of the liquid at 75 kilopascal. So that is 1.213 kilojoules per kilogram Kelvin. So we already have the value of SF4 and also the value of S4. So we need to get the value of SFG4. For SFG4, that is equals to the SFG at 75 kilopascal, and that is 6.2434. So therefore, by using the relationship, substituting those values that we have, we can get the value of X4. And X4, by solving for X4 in this equation, is 0.8857. So that means that at point 4, the quality of this two-phase mixture is 0.8857, or 88.57% is in a vapor state. So we can already get the value of H4 rather. First, we need to get the HF4 in the same way that we get SF4. So by using HF at 75 kilopascal, we have HF4 as 384.39. Also for HFG4, that is HFG at 75 kilopascal, so that is 2278.6 kilojoules per kilogram. So we have H4 as HF, which is 384.39 plus X4, and that is 0.857 multiplied by HFG4, and that is 2278.6. So our value of H4 is 2402.546 kilojoules per kilogram. So by summarizing the enthalpies that we have computed so far, we have H1 is equal to 384.39, H2 is 387.4241, H3 is 3115.3, and H4 is 2402.546. If you're going also to examine it, if it is really correct logically, first you should examine that H1 should be the lowest. So you can see here that among the value, H1 is the lowest, followed by H2. And that the highest of this value should be 0.3 because it has the highest temperature. So that's why we have H3 as the highest enthalpy, followed by H4. So it's always the sequence when summarizing the values of the enthalpies. So that is how you get the value of the enthalpies at the various points using the steam table. So again, this is just a recall how to get the value of enthalpies using the steam table. But we can also find the enthalpies at the various points in the cycle using the NIST software, which is the refrigerant property software. Water is also a refrigerant. That is why we can use that software to get the property of water, since steam basically is just water with different states. To make the finding of enthalpies at the various points in the cycle using the software easier, we will tabulate it. So in tabulating the values, you will label it first as the various points. We have the various state, the pressure, temperature, entropy, quality, and the enthalpy. You can also add other properties as may be necessary in the future computation. So on the problem, we have 4 points. We have point 1, point 2, point 3, and point 4. And by looking back at the given problem, point 1 is a saturated liquid, point 2 is a subcooled liquid, point 3 is a superheated vapor, point 4 the state is a mixture. We are also given that at point 1 the pressure is 75 kilopascal, at point 2 3000 kilopascal, the same with point 3 which is 3000 kilopascal, and point 4 is the same with point 1 which is 75 kilopascal. We are also given with the temperature at point 3 which is 350 degrees Celsius. So what we are looking for is the enthalpy by using the software. So we're just going to compare later on if there is a significant difference between the software and that of the steam table. So if you're going to open the software, you can find here that the default setting is nitrogen, and this is how the interface of that software looks like. So what you're going to do is to go to open it, just click OK until you can get at this point. Then you're going to click the substance, and in the drop menu, you can find there the pure fluid single compound. So just click that and click OK. Once you click that, you are going to find this fluid. Just go down and you can find water. Just click OK. After clicking OK, the default now will be, the setting now would be water. So make sure that when you're looking for the values, it will always be water here, because steam is just water anyway. After changing the type of substance, now we are going to set also the units. So just go to options, and then you can find in the drop menu the units. Once you click units, you will be going into this portions here where you can change the units of temperature, pressure, volume, and the other dimension by just clicking this drop box here. So I changed the temperature to degrees Celsius because the given is degrees Celsius, and also the pressure to kilopascal, so that I will not have to convert anymore. So once ready, you can click again OK. So after clicking OK, you can now use the software. So first, if you have to examine the different points. So there are only two things that you have to remember. So if it is a saturated liquid or a saturated vapor, so as long as it's saturated, you only need one property. When we say property, these are pressure, temperature, entropy, quality, and enthalpy. Those are the dimensions. However, if it is not saturated liquid or not saturated vapor, meaning it is a subcooled liquid, a mixture, or a superheated vapor, you need to have two properties in order to use the software. So if you're going to look at this given here from the problem, we have a saturated liquid, and we know that we only need one property if it is a saturated liquid. And here it is given as we have pressure of 75 kilopascal. So we can get now all of these properties using the software by inputting these values for the saturated liquid. So if it is a saturated liquid or saturated vapor, you're going to go to calculate, and in the menu you can find their saturation points. So just click that one, and then you will be redirected into this interface here. So in that interface, you will find here water and also saturation points. So this is where you're going to input the quantity that is known or the property that is known. And for point 1, that is saturated liquid, and we are given with 75 kilopascal. So just input that and just click enter. Once you click enter, the temperature and the rest of the properties will appear. So you just have to copy the properties that you require. So in my case, I will get the temperature. I will also get the value of the entropy of the liquid, since this is a liquid, saturated liquid. So I will get this one. This is saturated liquid. And also the liquid enthalpy, because this is a saturated liquid. So we are just concerned here are just the liquid, because this is a saturated liquid at point 1. So I will get temperature, liquid enthalpy, and also liquid entropy, and put that in the table. So I have the temperature, entropy, and the enthalpy inputted now in my tabulation. You can see here that the quality at point 1 is 0% because it is pure liquid. If it is a saturated liquid, there's no vapor at all. So meaning 0% vapor. We can also use the idea that the entropy at point 1 is the same as the entropy at point 2. So we can already copy the value of entropy at point 1 to point 2, and that is 1.2132. So you can see here, at point 2, this is not saturated liquid or saturated vapor. Therefore, we cannot use the same way that we got the value a while ago. So if it is a subcooled liquid or a superheated vapor or a mixture, we will use another way. So if this is the case, you will need to have two known properties. So in this case, we have two known properties, and that is the pressure of 3000 kilopascal and also the entropy. So that is the use of having the idea that the entropy is the same, because now we already have two properties, meaning we can use these two properties to get all of these values in the subcooled liquid region. So since this is a subcooled liquid, instead of clicking saturation points, you are going to go to calculate and click specified state points. So once you click specified state points, you will be redirected into this water specified state points. And then you will have to input the two known properties. So unlike what we did a while ago, that we only inputted one, here we need to input two properties. So that's why we have 3000 kilopascal as the pressure and the entropy of 1.2132. So once you click enter, you can get the temperature and also the enthalpy. So now we already have the temperature and the enthalpy at point 2. So you just have to copy these values here in our tabulation. You can find here that there is a very slight change in the temperature, because if you can remember, process 1 to 2 is just pumping. In pumping, you are not actually changing the temperature. So the change here could be because of some irreversibilities, but it is very negligible, or it is very small. So as you can see here, there is a very small change in temperature in pumping. Same also with the enthalpy. So a very small change in the enthalpy. So that is the reason why pump is better to use when you have this simple ideal Rankine cycle, because it requires little power input. Now we will proceed with point 3. Point 3 is superheated vapor, but the good thing about this is it has two properties already. We have the pressure and the temperature. So we will use the same way that we have a while ago. We will go to water specified state points and then just input the pressure and the temperature. So click enter, you can get the enthalpy and the entropy. So just copy this value in our tabulation table. So we have the enthalpy and the entropy. And finally, at point 4, we know that process 3 to 4 is isentropic process. So we just copy the value of the entropy at point 4. Now, even if it is a mixture, we still have two properties known already. So we just go again to the same process, specify state points, and input the two known values, pressure and enthalpy. Just click enter and you can find the temperature and also the enthalpy. So just copy those values. So now you can get the temperature and the enthalpy. You can find here that the temperature at point 1 and point 4 is just the same because they are just in the saturated region. So in this way, we were able to get all the enthalpies using the software. So if we're going to compare the results of the enthalpy using the software and the steam table, we can find that they are very similar and there is a very slight difference. So you can use either the software or the steam table, whichever is comfortable to you. But it's also very good to practice using the steam table for maybe in the board exam or in class. You may use this in that. So in our example, we will use the results in the steam table, but you can use also the result in the software. So we can proceed now to the computation of the other unknown quantities. First is the heat input in the boiler. So we need to get the heat input in the boiler. So if you can see, the heat input in the boiler happens in here at process 2 to 3. So this is where Qin happens. So Qin is just the difference between the enthalpy at point 1 and point 3. So that is H3 minus H2. So we already have the value of H3 and H2. So this is the reason why we calculated for the enthalpies. So we already have the Qn, and that is 2727.8759 kilojoules per kilogram. When you multiply it with the mass flow rate, you can also get the power input, and that is 95.48 megawatts. So this is the amount of power that the boiler produces from the combustion of fuels from solar thermal plant source or from the geothermal wells or from the nuclear fuel. So this is the heat input in the boiler. For the heat output in the condenser is between process 4 to 1. So that is just the difference between the enthalpy of 4 and 1. So that is Q out is H4 minus H1. So just input those values. You can find Q out as 2018.156 kilojoules per kilogram. In the same way, multiplying it with the mass flow rate, we can get the power that is being rejected to the environment as 70.64 megawatts. And then for the thermal efficiency, we can use the formula 1 minus Q out over Q in. We already have the value of Q out and Q in the previous result, so we can get already the thermal efficiency. So that is 26.02%. If you can see, that is a very small thermal efficiency. It means that 74% of the heat input is being wasted because only 26% is being used. For the turbine work, or that is the work turbine output, that is just the difference between the enthalpy of 3 and 4. So that is H3 minus H4. And substituting the value of H3 and H4, we can get the work turbine output as 712.754 kilojoules per kilogram. In terms of megawatt, we'll multiply it with the mass flow rate to obtain the power output of the turbine as 24.95 megawatts. So this is the power that is also coupled to the generator that later on would produce the electricity that would be distributed to the different users. The power output of the power plant is the difference between Q in and Q out, and that is 95.48 megawatts minus 70.64 megawatts. So the power output of this power plant is 24.84 megawatts. So it means that this is the actual power that is being delivered or that is being coupled to the generator that will be distributed to the consumer. We can also use the alternative formula, which is work turbine output minus the pump power input. So by substituting the values of those, we can also find that they are just the same with the first formula that we had. So you can use either of this formula in calculating the power output of the power plant. And then we have the heat rate. If you can remember, the heat rate is just the rate amount of energy used by the electrical generator or the power plant to generate 1 kilowatt hour of electricity. So the heat rate is just 3412 divided by the thermal efficiency. So we know that the thermal efficiency is 0.2602. So that's why the heat rate is 30,113 BTU per kilowatt hour. So it means that in order to produce 1 kilowatt hour, you need to produce 30,113 BTU of energy. Finally, another performance parameter is the back work ratio. So the ratio of the pump work to the turbine work. So by substituting the value of the pump work and the turbine work, we can find that the back work ratio is just 0.4257%. So it means that only 0.4257% of the work produced by the turbine is being utilized again by the operation of the pump, because the pump requires work input. So we're able to get the pump work, the heat input in the boiler, the heat output in the condenser, as well as the thermal efficiency. So if you can see here, our Q in and Q out are almost the same, or they are very near to each other. So that is not a good indication, because it means that you are producing a lot of waste energy here. We also have the turbine work, the power output of the power plant, the heat rate, as well as the back work ratio. So that is how you compute all those quantities in the simple ideal Rankine cycle.